Welcome to this course, Metallocene and Metal-carbene based organometallic compounds for polyolefin catalysts. Okay, so far what we have discussed, we discussed the Ziegler-Natta catalyst, that is the one of the very successful transition metal based catalytic system. Although it is a heterogeneous catalyst, but it was very popular, very successful, and the activity is quite good. Today we will discuss another category of metal based catalysts for olefin polymerization, that is the Metallocene catalysts. And after discovery of the Metallocene catalyst, is basically realized that this is a new revolution in catalyst science, particularly for the olefin polymerations, and many industries have been accepted this system. Obvious, there are a lot of reasons that we will discuss, and before that we will try to understand that what is the Metallocene catalyst system for the olefin polymerations, what are the components, and what is the initiator system, or what are the co-initiator system, and why this is needed, what is the role, and obviously the mechanism. And then we will discuss very systematic way what are the advantage which were not present in the Ziegler-Natta based another very successful catalyst, transition metal based catalysts. So the key points we will cover here: the Metallocene catalyst as initiator or catalyst, co-catalyst, the concept of the activation of the initiator, the mechanism of olefin polymerization. Okay, let's start. So now we are familiar about this kind of polymerations, where you saw that if you have a monomer like ethylene or any other alpha olefin, you can go do the free radical polymerization. So that we have already discussed in previous classes. Free radical polymerization, controlled radical polymerization, I am writing as FRP, this is CRP, then anionic polymerization, that is we call AP. The cationic polymerations are there, but not very common for the olefin polymerization. And then the coordination polymerations, that is the transition metal based catalyst system for the alpha olefin polymerations. And in the last category, that is the fourth category, we saw that Ziegler-Natta catalyst is very successful, and there we saw that what are the system, if you remember, yes, TiCl4 plus AlR3. Okay, and we saw that this is heterogeneous system, okay, and very difficult to understand the mechanism. Okay, the poor understanding of polymerization mechanism, and there, if you remember, that it is very difficult to understand, although we have realized that there should be a backflip of the whole polymer chain in from the growth side to the vacant side, that we have to make the vacant side at the original position where it was there before the propagation, and that's the way that we have realized that you can make the isotactic polymers. Okay, so the polymerization mechanism is really very complex and unclear, and also the heterogeneous system makes it more difficult to understand the mechanism. And also we saw that depending on the phase, crystalline phase of the TiCl3 like alpha, beta, gamma, delta, the stereoregularity is very different. Okay, so after the discovery of the Ziegler-Natta catalyst, people started to make a different system, or to develop a different system where you need to make the soluble initiator system. Why it is required? Because for academic perspective, if it is homogeneous system, the soluble system, then it is easy to understand the mechanism by different spectroscopic methods, which is not possible or very difficult either in heterogeneous system. Although if you think in a commercial perspective or industrial perspective, definitely the heterogeneous catalyst is the more advantageous. Okay, so homogeneous system, and to better understand, so these are the initial driving force to develop a different transition metal based catalytic system or metal based catalytic system. To better understand the mechanism, and obviously to develop more active catalytic system. You remember that when we discuss the mechanism of Ziegler-Natta catalyst, the polymerization happens on the surface. Okay, so in this case, because it is a heterogeneous system, the polymerization happens on the surface. The polymerization on surface. Now, if we make homogeneous system and soluble initiator system, then definitely the activity of the catalyst will be more. Okay, because now if now the molecules are, all the molecules are available, all the catalytic system or initiator available to initiate my monomer. So these are the three main driving force to or curiosity to develop a different metal system for olefin polymerizations. Okay, so before going to the main mechanism, I just try to give a flavor how this Metallocene based catalysts actually developed and discovered. So after discovery of the Ziegler-Natta catalyst, as discussed in the last slide, scientists jumped on to develop a different systems, and the group 4, and we discussed in very extensively the group 4 metals, that is the titanium, zirconium and bent metallocene. We have no lone pair. Okay, that is there is no non-bonding orbitals, and there is no lone pair. So it is a good acceptor for different ligands, as example like for ethylene, pi acceptor. So that electronic criteria we have discussed very extensively in our previous classes. Okay, so people started to develop new catalyst, and the category was very successful, where M is equal to titanium or zirconium, and this requires activation. So only this system does not work you have to you have to do the activation of this catalyst, and for that a Lewis acid system was used, and we will discuss later that what are the Lewis acid. I just try to understand, try to discuss the strategy. Okay. So, that time as we saw that for Ziegler-Natta catalyst TiCl4 and LET3, okay, their system, what was the problem? If you have some moisture, okay, in this system, it is a negative effect. Negative effect, that means it undergoes the hydrolysis and it actually gives the hydrolyzed product, hydrolyzed system, and the activity is remarkably decreased. Okay. So, why I discussed? So, from it is here it is clear that if I have a moisture in the system, then it is bad. So, same concept or same experience was also applied, that if I use any kind of moisture or in the system, then there may be a problem. So, here initially what was done, Cp2 TiCl2, okay, using Me2, that was the first discovery of the Metallocene catalyst, or the attempt of discovery of the Metallocene catalyst, that when this system was used in the presence of Cp2mx2 plus LET3, okay, or you can in general AlR3, okay, that there was no polymerization. There was no polymerization. Please note it very carefully. Okay. So, what is the wrong with this one? People are confused. Okay. Then it was the two scientists independently, Breslow and the Natta, reported that if you take this system and plus a little amount of water, okay, then if you do the polymerization like ethylene, then the polymer was detected. Okay. So, this was a really very confusing, and at the same time it was really funny. So, then it was realized that this water has a positive effect, which is unlike in the Ziegler-Natta system. So, this one actually reacts with water and give like this kind of dimeric system. That was actually Breslow independently and Natta, actually two scientists, Newberg. This is around in 1957. Okay. Now, with this idea and this observation, Natta later observed that if you purposively take some moisture, so his system was zirconium and dimethyl, and we will discuss this in more detail. I just want to show how it was developed. a very nice story is there. And then if you use like, so is a trimethyl aluminum, and then purposively little water, okay, and you saw that if you do the polymerization, okay, then you see that activity is much higher and is much higher, even is higher than the Ziegler-Natta catalyst. So from this, and this was discovered by Seen and Kaminsky. Kaminsky was the pioneer in this Metallocene catalysts, and this was discovered in around 1980. So you see that the chemistry is not really very old. So this was the you can say the renaissance in the polymerization in the olefin polymerization chemistry, and this is after that the many industries started to follow. Obviously, there is a lot of reason that we will discuss. Okay. In you see here in the Breslau and the Newberg and Natta, they took this aluminum compound, and Seen and Kaminsky, they actually took this one, that is the halogen free, both cases. Okay, here also halogen free, here also halogen free, that is more advantageous than the others. Okay. So this is really very important observation by the different scientists. Okay. So here you see that if you take that only this one, there was no polymerizations or very little, okay, you can say, okay, negligible. But if you take this kind of aluminum compound in with your metallocene, titanocene or zirconocene catalyst, and if you purposefully add little water, then you saw that there is a drastic change in the activity. And Seen and Kaminsky proposed that this one undergoes a partial hydrolysis and then gives a different oxo-bridged aluminum clusters, which is popularly called MAU. We will discuss in very details, okay, about the MAU, because it has a big role in catalytic activity. Okay, fine. So so you will see that different how the active different catalytic systems were developed, and in a very systematic method, and which was a kind of a revolution in polymer industry. Okay. So you here, if you recall, you have discussed in the previous class, so I will not go in very detail. If you just recall our last classes, that there is some structural parameters. Here this is the our, if you can just think that this is my Me2, or this is the structure of ZrX2, and here you will see these are the bent metallocenes we all discussed, and this one you will see that if you draw the plane angle, okay, the plane of the separating are meeting here, and this is the beta. Similarly, this also if you draw this one, and this is the bridging atom. So here you will see the more beta or more phi is means the more openingness of the sandwich structure. Okay. So this, if this is more, then here is more openingness, means the steric factor is less here. That means substrate, that is here monomer, can approach very easily. So, different type of ligands we already discussed, not only the CP rings, different fused polycyclic ligands can be incorporated, bridging or non-bridged, and we will discuss later where we have to bridge, where which is actually falls in the category of the Mansa metallocene, that we will discuss. Okay, fine. So, we now know that the Kaminsky developed the first active catalyst, metallocene based catalytic systems, that is the Cp2Z@Cl2 or Cp2Z@Me2, okay, and in presence of the MAU. Okay, we will discuss in the next slides what is the MAU, and you saw that there is a polymerization, smooth polymerization, and acts as a fantastic system. Even in some cases the activity is much better than the Ziegler-Natta catalyst, and it is a homogeneous. So, it is very easy to understand the mechanism, and the complexity is not involved much as we have seen in the Ziegler-Natta. Okay. So, later after discovery of the polymerization, then Kaminsky and other groups were now interested how to regulate the stereoregularity. Okay. So, that is the one of the challenge, okay, because if we make the stereoregular polymer, and if we know that what is the mechanism, how and accordingly if we can design the catalyst, then we will have a kind of a toolbox, that if I need a isotactic, I will use this catalyst, if I need a syndotactic, I will use this catalyst, if I need atactic, I will use this catalyst. So, with this target, okay, so what was the concept? So, if you see that this catalyst, okay, that is the zirconium, okay, and okay, like if I draw like this one, okay, if you see that these two CP rings are symmetrical, this is achiral because you have a plane of symmetry here. This the plane, okay. So, this is achiral. Now, if I make chiral, how we can do it? I have to destroy this plane of symmetry, okay. And how we can do it? We can do it by using two different CP ligands. So, with this target, this one done. So, one in case CP star and one in case CP, fine. So, if we also different like this one, if it is my different group, okay, this is the, let us say I am changing now this one, okay. Just it will be more clear now. If I put like this is Me, okay. Now, what is happening? If we change substituents of the CP as well as the this one, then what will happen? You don't have plane of symmetry of this one, and also you don't have plane of symmetry this one, okay. This is basically the, if you consider these two CP rings like this one. So, if you consider a plane, okay, here, then so if you consider the plane of these two planes, okay, this is one chloride and one is methyl. So, if you consider two plane, then also it is not symmetric because you have a chloride and you have a methyl. So, here now this is now achiral. Now, you see after using this one also, the Kaminsky observed atactic polymerization polypropylene if you use the prochiral monomer, fine. So, it is very interesting, okay. So, even though we are using the even though we are using the chiral catalyst, then also you are getting the atactic polymer. Okay. So, when 2Cp and 2X, it was achiral, and when 2Cp's are different and when one using X and one using R, then it should be chiral. Okay. So, if you use the chiral catalyst, it polymerization should go through the catalyst site control. Okay. Then my polymer should be isotactic polymerization, that is I should get the isotactic polypropylene, but in this case you see we are getting the atactic polymerization. So, this is also kind of a very confusing. However, later realized that due to the rapid exchange and rotation, and this rate of exchange and rotation is much faster than the insertion of the alkene, and due to this one is actually it is undergoing the atactic polymerization. So, what to do? We have to stop this exchange or the rotation, and for that one, how we will do it? We have to bind the two Cp rings. Okay. So, you have to bind the two Cp rings, okay, by some bridging unit. Then what will happen? You are stopping the exchange and rotation. Okay. And by that way you can get your desired isotactic or syntactic polymerization depending on the symmetry of metallocene. So, that is the one of the beauty in this metallocene based catalytic system. So, you depending on the symmetry and structure of the metallocene, you can get your desired atactic, syntactic, isotactic in very controlled way. So, that is the one of the biggest advantage of the metallocene based catalyst. So, you have to be a good concept on the symmetry and the point groups of the metallocene. Okay. Fine. So, here we know that polymerization by metallocene catalyst now can be done with the two systems. One is the Cp2, this is my called the main catalyst, and this is also it is needed, this is called the co-catalyst, okay, or sometimes it is called initiator and it is called co-initiator. Okay. First what I will do, I will just discuss the polymerization condition, and then after from that condition we will try to realize what is happening and what are the criteria of this polymerization. So, if you take the monomer like ethylene, so you will get the corresponding polyethylene. Okay. Now, here two catalytic system, one is you need the catalyst and you need the co-catalyst. Now, it is very clear. Fine. Now, generally we used a hydrocarbon solvent for the polymerizations if your monomer is gaseous. Okay. And here this co-catalyst is used in a large excess like 1001 to let's like that. Okay. So, this is the ratio of your MOU. I will go detail what is the MOU. So, this is actually called the MOU. Next slide I will discuss the detail about the MOU, and this is the zirconium. So, your co-initiator and initiator, real initiator ratio is quite high. So, that means this MOU is used, okay, in large excess, and this has to be added first. This is very important. In the polymerization vessel, you have to use this one as first, and it is believed that it destroys the impurity, if there is any impurity in metallocene. If you use the reverse, that is first the metallocene and the MOU, then if there is any impurity, that impurity will not be taken care of, and you can get the less polymerization activity. Okay. So, that is very important. Okay. This has been realized after trial and error. So, if you take the first, if added first, polymerization will be lower, and metallocene may be destroyed in presence of impurity that come from the solvent or the polymerization vessel. So, that is very important. Okay. Fine. So, you realize here that you need really a very good amount of MOU. So, now let us say what is MOU. Okay. So, as I told that this is a co-catalyst, you have to use it, only metallocene cannot perform the polymerations. Okay. And this MOU is nothing but the partial hydrolysis of the trimethyl aluminum, that is the we call trimethyl TMA. Okay. So, this is trimethyl aluminum, and if you do the polymerization, if you do the hydrolysis, that has to be controlled hydrolysis, that means partial hydrolysis, then you will get the structure of like this one. Okay. So, that is called the methyl alumino-oxane. Okay. That is nothing but the MOU. Okay. Although this is a very simplified structure I show, it is a linear, but in reality it is not that simple. It may be linear, it may be cyclic, or it may be three-dimensional, network structure. Okay. And most people believe that this is and it accepts that it is a cage like structure. Okay. So, what happened? You have like this kind of cage like, I am just very qualitatively I am showing, and this is you have a like a aluminum here, aluminum here like this one, and like that. Very qualitatively I am showing like this one, and the activation of the catalyst is actually happens on the surface here, activation of catalyst. Fine. So, you see that this is really a very complex structure although, and this is acts a very good Lewis acid, and that actually we need to activate the our main catalyst, that is the zirconation. Okay. So, so far what we have understood in this class, we understood that there is a need of more reliable and more efficient catalyst than the Ziegler-Natta catalyst, because although Ziegler-Natta catalyst was very successful in olefin polymerization, and the disadvantages of Ziegler-Natta catalyst we have now discussed very elaborately. To remove all these disadvantages, the scientists started to develop a new catalyst, and the Metallocene based catalysts were proved to be one of the best substitute of the Ziegler-Natta catalyst. Reasons are various, that some of we have discussed in this class, some of the we will discuss in the next classes. So, as you know that here the catalytic system, two component, one is the catalyst and the co-catalyst, and we have now know that what is the co-catalyst, and in the next class we will try to discuss the role of the co-catalyst, how the activation happens on the main catalyst, and how the polymerization growth happens on the Metallocene based catalyst, which is called also as a single site catalyst system, and why it is called the single site catalytic system. So, in the next class we will continue this Metallocene based catalysts and its detailed mechanism. Thank you. See you in the next class.